This is Markarian. This video is on the ideal gas law. So we're gonna do a quick little tutorial on how to solve problems with the ideal gas law, what it is, that kind of stuff. And then we'll be meeting for Zoom at 1 o'clock Tuesday and Thursday to go over some more practice with you guys if you need it, and I'll take questions and things like that. So let's dive in. The ideal gas law, I mentioned a few weeks back and all throughout, our time with the mole, that eventually we get to a point where we're not at STP and trying to figure out numbers of moles and things like that. And this is that time. Okay. So the ideal gas law is PV equals nRT. We say pervnert for short. It's like, I'm not the one that made that up, by the way. So, but usually chem teachers call it pervnert or pervnert. P is for pressure, and that's usually going to be in ATMs for our calculations. The V is the volume, which is in liters. N is the number of moles, okay, which is MOL, okay. And when you look at the R is a constant, and gas constants are used to help us get our units to work out, and things like that. And during the Zoom, I'll tell you how we calculated this number, but they actually, just real quick, they plugged in the numbers for STP into this thing. 1 mole, 1 ATM, 22.4 liters, and 273 Kelvin. And if you do the math on that, you get 0.0821. So it's a constant that helps us cancel units out. The T is the temperature, and that's, as always, in kelvins, okay? I refer to this as a snapshot law, meaning this is a law that is like right now, what are the conditions for the gas? The laws we've been looking at before this were before and after laws. So you had conditions before, that was the P1, the V1, and then you have the conditions after P2, V2. This one is just, hey, this is what's happening right now. Okay, and it's really good for doing stoichiometry problems that require, the mole. So a couple of things. We make some assumptions about ideal gases. These are not true, but they make life easier in the calculations. And I'm not going to go too deep into this, but ideal gases have no particle volume of their own. We're assuming that. Okay, so they take up the space of a gas, but each of the little particles in that space, we assume, have no particle volume. Okay, and that really helps, as you're going to see. Ideal gas particles, we also assume they have no attraction for each other. So even though, they are attracted, we talked about this in first semester with intermolecular forces of attraction, IMF. We're assuming those aren't there for the calculations. If we don't make those assumptions, PV equals nRT looks like this, which is a nightmare. We don't even do this in AP Chem anymore. They got rid of it. So we don't have to do that. We have a very simple equation now. Okay. So let's look at a typical ideal gas law problem. I don't know what happened here. There we go. Okay. So it says a 3-liter rigid flask contains 2 moles of argon at 300 Kelvin. So I look at this problem, I see 3 liters, I see volume. There's the V. I see moles, I see little n, which is number of moles. Okay, and I see a temperature, T, and it's asking for P, the pressure. So I have my setup here, PV equals nRT. I'm going to get P by itself, which means divide by V on both sides. And that's going to cancel out and give me this guy. Okay. So I've got everything set up. So then all I have to do is go and plug everything in. Now the R is given to you on any assessment. When we do this, in regular conditions for school, it's always given to the students. It'll be given to you if we do any online assessments or anything like that. So we have 2 moles times the 0.0821. Notice it's atmospheres, liters times over moles times kelvins. Let's do the cancellation of the units. So the moles here cancel the moles there. The liters here cancel the liters here. And the kelvins here cancel the kelvins there. And guess what we're left with? The R constant is magic. It's literally mathematical and chemistry magic because it gives us the units that we need when it's all done. So we do the math, this times this times this, divided by 3, and we get 16.4 ATM. Okay, so we got the pressure of the gas in those conditions. And that's, once you get down that idea, again, go back to what we've talked about in other laws, label it like we're doing here. Okay, figure out what's what in the problem itself, figure out what they're asking for, do the algebra that you guys, Probably not your favorite, but it's useful. Okay, it's a tool that we use. So we have that. So that's a couple of examples and what the ideal gas law is. During the Zoom meeting, we're going to go over a couple more that I have in the notes. We'll have a little more time to go through some of these, and we'll talk about how to set those up. And then I'll give you guys a couple in the Zoom meeting here that you see in the notes. And then our next topic will be Dalton's Law of Partial Pressure. So I know on the calendar it says climate change review next week, but we're going to go ahead and stay in gas laws for a little bit. Once we get through gas laws, then we'll switch over into climate change and go from there. Okay, hang in there. We'll get through this as always, and I'll see you guys soon.